Welcome to Zero Knowledge, a podcast where we explore the latest in blockchain technology and the decentralized web. The show is hosted by me, Anna.
And me, Frederick.
In this week's episode, we catch up with Alan Szepieniec, a co-author of the Supersonics and Marvellous papers. We talk about his work on SNARK constructions and hash functions. So today we're sitting with Alan Szepieniec, who's a researcher at Nervos and is also the co-author of Transparent SNARKs and Dark Compilers, the Supersonics paper, and the Marvellous paper, which specifies the vision and rescue hash functions. So welcome to the show, Alan.
Thanks. Well, I'm glad to be here.
And we also have Frederick.
Hello, hello.
I think I'm curious to hear a little bit about your journey kind of into cryptography and how you got involved in these various topics.
Actually, the first story I can tell is when I started learning programming in C back when I was 10. One of the first programs I wrote was an encryption program. With the hindsight of having the PhD and stuff, it wasn't a very clever encryption algorithm, but still, it shows that I was interested from a very young age already. When did I get seriously interested? I would have to say that was at university when I started studying applied discrete algebra. And it was just so cool what you could do. And we learned how RSA works, and I implemented RSA. And it was really exciting science. But aside from the exciting science aspect, there's also the privacy aspect, which I really like. I think cryptography is in the intersection between exciting science and technology that can enhance human freedom.
Cool. Where did you actually study?
I studied in Leuven, which for me was conveniently the closest university to where I was living, or where my parents were living, because when I went to university, I stopped living with them. It was the closest university conveniently, and I studied computer science and electrical engineering for the bachelor's, mathematical engineering for the master's, and that was really not very well linked to cryptography. Mathematical engineering is more about numerical algorithms, optimization, control theory, machine learning, but for my master's thesis, I picked a cryptographic topic, and that's how I got into cryptography intimately. And then after my master's, I started looking around. I knew I wanted to do a PhD on cryptography, and I thought maybe it's time to leave Leuven. But then when you look at the places where you can do a PhD on cryptography, Leuven is maybe not number one on the list, but certainly up there. So I decided for the time being, it's worthwhile to stay in Leuven.
Yeah, we had Nigel Smarts on the show, and I was just thinking it's a very convenient university to have close by, especially if you're on the cryptography path. And Nigel had nothing but good things to say about the university. And
I can imagine that had I gone to another university, I would have been more interested in another topic. There may have been some influence from the research group appealing to students in the master's program.
Cool.
Yeah, it's kind of interesting to see how different universities kind of get their niches, and they establish their own vibes and what they focus on. But I imagine it is sort of an internal, once you catch on and a university gets good at something, it's like a self-perpetuating kind of thing where now that department promotes to all the students that they should get involved with this.
It's like how ecosystems kind of emerge, actually. It's also this actually reminds me of how music scenes emerge. I know this is a very strange comparison, but I'm from Montreal, and I remember few years ago, there were some really good bands, and then all of a sudden it became a hub. Everyone moved to Montreal to play in bands. And I imagine this kind of thing must happen in universities where just a few really shining stars emerge, and then around them, there's like an ecosystem that forms.
Yeah, I think that's accurate. It's a self-reinforcing circle.
So what were you studying when you did your PhD at Leuven?
When I did my PhD at KU Leuven, I studied post-quantum cryptography, and I specialized in multivariate quadratic systems. So in post-quantum cryptography, you have a couple of branches of mathematics to choose from. And multivariate quadratic cryptosystems, the idea there is that your public key consists of a list of polynomials of degree 2, but in many variables. And in order to encrypt or to verify a signature, you just compute the value of the polynomial in a point. And this point would be your plain text, or it would be the signature. You just compute the value of the polynomial, and that gives you, since there are a list of polynomials, that gives you a list of values, and you check that against the hash of the document that you're signing, or you send that as the ciphertext. And then the whole clue for being able to generate a signature or being able to decrypt is to generate this initial list of public polynomials in such a way that there's a trapdoor embedded that you only can exploit if you know the secret key, so that from the point of view of the attacker, your public key is just a random list of polynomials. But if you know the secret key, then you know how to invert it. So that means that you know how to generate signatures or find the plain text according to a ciphertext.
That idea of, I mean, we've touched on the post-quantum idea. I'd be curious to hear from you. Do you think it's very, very urgent to create post-quantum security systems today? Or do you think that it's still very theoretical and post-quantum computing is very far off, so we have plenty of time?
I think the construction of quantum computers is progressing at a pace that is independent of the progress of media reports about the progress of quantum computers. So you have to ask a physicist who is really deep into the field in order to assess where we're at in terms of quantum computers. I don't trust the media reports at all. The times that I've spoken with physicists or that I've heard them speak, they tend to be optimistic. They tend to say we'll have something that's interesting for cryptographers within 10 to 15 years. I think they may also be required to say that by the budget office. So my cynical position is that we'll have something interesting to cryptographers between 20 and 30 years, and 30 years from now, we should have switched properly to post-quantum cryptography.
Got it.
Some people are skeptical that quantum computers could exist at all, and I don't belong to that camp. I don't think that nature is malicious enough to deny us the possibility of quantum computing.
Got it.
I think the main thing to be, like, quantum computers already exist, right? So the main thing to be skeptical of is, like, to what size can they grow? Can we make a desktop quantum computer and like things like that? Because, you know, can we ever find the materials and everything to make a quantum computer that doesn't require near zero Kelvin cooling and all these kind of things? So
yeah, what you mentioned here, the near zero Kelvin cooling, it reminds me of just the sheer scale of the engineering problem, because in order to control your qubits, you have to have actuators that still operate at near zero Kelvin. And well, that's a classical engineering problem. You don't need any quantum mechanics to engineer these actuators per se in such a way that they're still operational at near zero Kelvin, but it's just a problem that we've never encountered before. So that's one of the reasons why I think quantum computers will come. It's just going to take a lot more engineering than we expect.
I think what we should do now is chat a little bit about your work on like some of the papers that you've been co-author of. At Leuven, like you did your PhD, but did you then leave Leuven and do a postdoc, or like, because you've been involved with the transparent SNARKs from Dark compiler paper. So this is a paper that has Ben Fish and Benedict Bunz and yourself as co-authors. So were you doing that from Leuven, or did you do that after? Like when did that happen?
So after my PhD, which was in December of 2018, I was postdoc at KU Leuven for a very short period. And then I started to work for Nervos. And then a couple of months into working for Nervos, I moved to Switzerland, which is where my firm was set up. And well, that makes sense for me to move here. I started working on the Dark compilers paper right after Eurocrypt 2019. I'm not sure when it was exactly anymore, but I remember that I was still in Leuven at the time, but I was already working for Nervos.
So that's earlier this year, I guess.
Earlier this year, yeah. We had a very rapid product development life cycle there.
Cool. Yeah, that's great. I mean, there's so much research coming out right now. I think for our audience, I actually have a video on YouTube of Ben Fish presenting at least like a half-hour presentation on this topic, which I can link to. But maybe you can share a little bit, like, what is Supersonics? What is this paper all about?
I think the best way to answer that question is to look at the history of how this came about. How it came about was at Eurocrypt, I was discussing with people and I was saying what Nervos wants is really a proof system that's efficient to verify, but has a public key setup, or a transparent setup rather. So there is no trust assumption in the setup. But it should still be efficient to verify, and in fact, zero knowledge is optional. And it was clear from the conversations that I had at Eurocrypt that the SNARK proof system was the only one that came close, except the size of the proofs were still rather large, or I think they've managed to shrink them down quite significantly in the meantime. But at the time, we were looking at 500 kilobyte proofs. And I was wondering, well, the only cryptographic ingredient there is a hash function, which is really cool from the point of view of post-quantum cryptography, because we don't know how to attack hash functions efficiently on quantum computers. But, well, what if you don't need post-quantum proofs? Then maybe you can use a different cryptographic tool to reduce the size of these SNARK proofs. So that was the question that I was looking at. And then I was simultaneously looking at Ben Fish and Benedict Bunz's accumulators paper, which is using class groups to generate efficient accumulators. And the ball started rolling from there. I thought, well, what if you start using class groups to do these polynomial evaluation proofs? Well, actually, what SNARK is doing is it's showing that the polynomial that is committed to has a sufficiently low degree. But I was looking to enhance that protocol a little bit, and then I came up with something, but then I didn't know how to prove it, and I didn't know what else you could do with it. I had a strong intuition that you could build SNARKs out of this protocol, but I really didn't know how to proceed. So I reached out to Benedict, and he recommended to bring Ben on board as well. And then Benedict, he told me how to prove, or well, actually Benedict proved the security straight away, or he saw early on how to prove the security, and that was cool. And then Fish, he thought, okay, let's think about this logically, or analytically rather, what kinds of things can you do with a polynomial commitment scheme, which is what the protocol achieves, right? You commit to a polynomial, and then the verifier specifies a point, and then the prover proves that the committed polynomial evaluates to a given value in that point. And then the answer to Ben's question seems to be, well, we can actually capture a lot of these SNARKs, or rather, we can capture a lot of the machinery underlying these SNARKs in terms of polynomial commitment schemes. And then we can reuse the same machinery and compile it down using our class group's polynomial commitment scheme to achieve a new SNARK proof, one that doesn't have a trusted setup, but still does have an efficient verification. So there are a couple of options there. We can start from the machinery underlying the STARK proof system, or we can start from the machinery underlying the GGPR type SNARKs, or we can start from the machinery underlying Sonic, which is what we focused on at the time. And it was obvious that from the point of view of optimizing for trustless setup, the result was going to be an improvement over Sonic, which is why we called it Supersonic. Fortunately, or unfortunately, depending on your perspective, right around the time when we wanted to publish the paper, other people came out with Plonk.
Oh, yeah.
Which is similar to Sonic in the sense that it is a universal, one-time trusted setup. And then other people still came out with Marlin, which is also in the same category. So we decided to say, well, you can compile any one of these three proof systems with our class group polynomial commitment scheme, and the result is still called Supersonic. So technically, Supersonic refers to three slightly different proof systems.
So Supersonic is also Super Marlin and Super Plonk.
Exactly.
Got it.
So I'm curious, like you say, it's an improvement on the system, but is there a trade-off? Like what am I, in order to get the non-trusted setup, what am I giving away? Yeah.
So the proof size increases. That's not so fun. So for Plonk, I think the proof size is just over 1 kilobyte. Don't cite me on that one. But the nice thing is that the proof size is independent of the computation. Whereas when you drop the trusted setup, then the proof grows logarithmically with the size of the computation. So we're looking at proof sizes that are about 10 times larger than you can get with pairings. That's one trade-off. And then the other trade-off is we don't know much about the security of class groups. These objects have received very little study. They've been known for a while, but they were always thought to be outperformed by elliptic curves. So nobody cared. But the big difference is that elliptic curves have known orders. And once your order is unknown, then you can do all sorts of fancy tricks. So the security is a second trade-off. You would trade the security of pairing groups, which are also up for debate, but arguably less so than the security of class groups.
Yeah, we talked a little bit about this with Joseph in the recent VDF episode, but there is an active area of study of class groups now and trying to optimize it, trying to create hardware for them and all sorts of other things. So I mean, when you say it's a security trade-off, well, it's a trade-off in the cryptography sense of like it hasn't been studied for 30 years kind of security. not that we know that it has a weaker security, right?
Correct. Although there is a qualitative distinction to be made, namely that elliptic curves, and I should make an explicit exception for pairing-based elliptic curves, but if you look at regular elliptic curves, the type of elliptic curves that you can use in conjunction with bulletproofs, there we don't have sub-exponential attack algorithms. So you can choose the order of the elliptic curve to be twice your security level, and you won't be able to do any better than that. And that's really cool. But once you move towards pairing-based groups or class groups, then you start having to deal with sub-exponential attack algorithms, and you have to choose the size of your parameters to be larger to take into account those attacks.
At the most recent Zero Knowledge Summit, Alessandro Chiesa kind of helped to map out a lot of these new constructions, and the framework that he used had been, and I think actually Ben Fish had mentioned to me a sort of similar thinking, which was like thinking about these SNARKs or SNARKs as having a front end and a back end, and I don't know if I'm going to remember this correctly, but I think like Planck and Marlin might be living in the back end, and the supersonic element lives in the front end, or vice versa. It's something like they're basically optimizing on kind of two different fronts. Exactly.
And what you call the front end or the back end, that depends on your perspective. But the key technical contribution of this paper is all the way at the end. It's just changing the cryptographic step. So in the end, you have to choose between Merkle trees of Reed-Solomon code words. That's the strategy employed by Stark, Aurora, Fractal. Or you have to choose for pairing-based groups, and that's what Marlin, Planck, Sonic, GGPR do. And we provide a third option. You can do the same thing based on class groups. And only the second option, pairing groups, comes with a trusted setup.
So I think to really understand this construction, I think it's really good to get a lot of background. So as I mentioned, there is this talk by Ben Fish that I have on the YouTube channel. P.S. I'm going to be sharing all of these links in the show notes, so please just check that out if this is interesting to you. I'm going to provide a lot of extra information. There's the paper, there's a talk, and there's also talks on Planck and talks on Marlin. And so then you can start to see how these things can all work together. Yeah, I think it's a very, very interesting time for this kind of work. And this paper is definitely like a highlight. Let's now go on to a second paper that we wanted to talk about in this podcast, which was the Marvellous Vision Rescue Hash Function Specification paper. So is there anything, maybe before we start in on this, that you think listeners should sort of keep top of mind or maybe do a little background research on to understand Marvellous?
If you want to understand how the hash functions work, you really need finite fields, and with that background, you can start implementing the hash functions. If you want to understand why they are secure, well, that's a different matter altogether. You definitely need background in linear algebra, multivariate polynomials, and so on. But in the end, one of the points of this paper is that the security of these type of hash functions is still a very much open question. So even we don't know how to assess the security accurately, although we do have a couple of threads that we're exploring inside the paper.
What would be comparable? Like what does the Marvellous hash function try to be better than?
Yeah, maybe if we start out with just what are the objectives, and in the abstract of the paper, I think you expressed this reasonably well, but starting from that level, what is it going for?
The first question is obviously, why do we need another hash function, right? We already have SHA-2, and maybe 10 years or 15 years ago, we thought SHA-2 was going to get broken, but 15 years later, we're still nowhere near breaking SHA-2. So SHA-2 is fine. And then catchup is fine as far as we know also. And if you want something even faster than catchup, then you can go to Blake 2. And that's fine as far as we know as well. So why on earth would we need another hash function or another pair of hash functions? And the answer is that when you want to implement SHA-2 or catchup or Blake inside of a zero-knowledge proof or inside of a multi-party computation, then the complexity of these protocols blows up. And that's because the specifications for SHA-2, catchup, Blake, they all use operations that are not native to any finite fields.
They're optimized for CPUs, essentially, right?
Exactly. They are optimized for CPUs, for RAM machines, or for embedded devices, for hardware. It doesn't make any sense to reduce the number of field operations with that metric in mind. But when you're going to implement something in a zero-knowledge proof or over multi-party computation, you want to reduce the complexity of this protocol by as much as it is possible, and then you want to shun all possible non-native finite field operations. That research question was already raised in a couple of earlier designs. There was LowMC and there was MIMC, and our designs fall into the same category.
So essentially, instead of optimizing for CPUs, you're trying to optimize for arithmetic simplicity and making these easy to compute in a zero-knowledge proof.
Exactly.
How much easier are they to compute in a zero-knowledge proof? Like, what are the results?
In order to compute something stupid like a bitwise rotation over a zero-knowledge proof, you have to express this rotation as a sequence of finite field operations, which only gives you additions and multiplications. And in the end, this very simple operation turns into a very large polynomial. And in practice, we think the difference will be factor 100 or 1,000, depending on which exact choice you're using for the traditional hash function and arithmetization-oriented hash function.
Yeah. Is this at all similar to what Zcash did for their recent optimization of their zero-knowledge proof, where they switched from SHA-256 to a Peterson hash? And that was like one of the reasons. There were a lot of reasons for the speed up in this upgrade, but that was one of the main reasons. But a Peterson hash is not the same as the hashes you're talking about. But is it still trying to do that thing where it's like trying to simplify and optimize for arithmetic complexity rather than CPU complexity?
The objective is the same, correct. I think Peterson hashes, well, you can define them over finite fields as well, but the idea is you take a sequence of group elements, typically on an elliptic curve, typically random group elements without mutually known discrete logarithms, and then you take your message, divide it into bits, and the bits indicate which group elements to multiply together. That's arithmetically very efficient, but this hash function doesn't satisfy all the properties that standard hash functions have, like pre-image resistance, second pre-image resistance, collision interactability. The goal in this paper is to create a hash function that provides the same properties as standard hash functions. Whereas Peterson hash functions you can use in certain contexts, but you can't use in other contexts.
So it's a bit more of a generalist solution, I guess.
Correct. But it is possible that Peterson hashes will outperform our designs in certain scenarios.
Got it. Would there be other types of hash functions that you would compare or contrast Marvellous hash functions with?
Well, there are obviously, cryptographic functions like block ciphers and verifiable random functions and public key encryption, but I'd say it's the most similar to traditional hash functions like SHA-2, except with this one big caveat that the complexity metric is different.
You mentioned zero-knowledge proofs as an application for this or a context that you'd use it in, but are there other applications? Is there other areas of cryptography where this property is desired?
There are. the observation that makes general purpose zero-knowledge proofs work is essentially the idea that you can express an arbitrary computation as a sequence of finite field operations. This is called arithmetization. And it turns out that arithmetization is also the operating principle behind multi-party computations, behind fully homomorphic encryption. And there's even a fourth example, namely functional encryption, although we don't have functional encryption for arbitrary depth circuits. It still provides you additions and one multiplication. These are all over finite fields. So then the question is, how do you express an arbitrary computation like machine learning over shared data sets in an MPC setting as a sequence of finite field operations? And the answer is exactly the same as in the case of zero-knowledge proofs. So is there ever a case where you need to evaluate a block cipher or a hash function over MPC? We expect there is. For instance, if you're going to run a machine learning computation over MPC, and then you want to encrypt the result so that only one person can read it and the other participants can't, well, you want to perform this encryption on secret data. So you have to evaluate a cipher on secret data. So you have to evaluate it inside of your MPC protocol. Another example is if you want to thresholdize deterministic signatures. So signature schemes like Schnorr and ECDSA, they start out with a commitment to a nonce, which is just g to the power random number. And that's actually the first component of your signature. And it so happens that this should be random, because if the adversary can guess it, then he can forge signatures. But once you sign two different messages with the same nonce, then you lose your secret key. So you should make sure that you never use different nonces to sign different messages. And a very straightforward solution there is to just take the hash of the document that you're trying to sign and concatenate the secret key before you take the hash, right? You take the hash of both, and that's your nonce. That's a perfectly valid solution. It generates a deterministic nonce, which from the adversary's point of view is as good as random. Except that only works for a one-party computer. When you want to spread your secret key across multiple parties, and you want to apply the same trick, you still want to get a deterministic nonce, so you need to compute the hash of the secret key concatenated with the document, or the document concatenated with the secret key. So you still need to compute the hash of secret data, and you might as well use one of our ciphers to do that.
Cool. And this is definitely like signing things in MPC is like a hot topic and a thing that everyone wants to do now. That seems pretty relevant.
Correct.
What are those ciphers that you just mentioned?
Schnorr and ECDSA are signature schemes. Schnorr has been around since 1990, and I think it was patented really, really soon after publication. And then ECDSA was standardized as a way to get around the patent, but it uses essentially the same mathematics. It generates really small public keys and generates really small signatures. That's really cool. And because of the patent, I think Bitcoin had to use ECDSA when it launched, but the patent has since expired, but we're still stuck with ECDSA on Bitcoin, which is a shame because Schnorr signatures are better because they allow you to do fancy things like signature aggregation and stuff.
Like native multisigs and not having to go through Bitcoin scripts to do a bunch of stuff.
Exactly.
It's funny that like Schnorr signatures on Bitcoin has been this hot, like it's been a point of discussion for so many years now. And like for a while, it really looked like it was going to get in and like they were going to get it. And now it's just like, nah, fuck it. Bitcoin's not going to do anything at all. Yeah, it's a shame.
Yeah, I think it's indicative of the whole selling point for Bitcoin in the first place, which is that it's supposed to resist change. It's supposed to be difficult to change. That's why I can be reasonably confident that my money will still be there in 20 years. It would be far more disconcerting if they could change it at a whim, because then where do I put my money?
Do you think the original, this is like sort of a side tangent here, but do you think the original idea really was that conservative? Like, was that built into it from the start to be like, we're going to build this thing and then it won't change? I feel like this is something hotly debated in this community.
Yeah, it is hotly debated, and if you look at the very early days, there were plenty of changes. The first few emails sent out by Satoshi are literally bug fixes or announcing bug fixes, and a lot of those bugs were consensus critical. So yeah, the protocol did change, but then it really only changed in the beginning and not really that much afterwards. Or at least afterwards, we've only seen soft forks, which aren't really forks. I don't know. I'm not Satoshi, and I'm not in his mind either.
Or their mind.
Or their mind.
Actually, so the question that I had before was a little bit more about your ciphers. Can we dig a little bit into the ciphers that are actually within the Marvellous hash construction?
Right. So I think the best way to explain this is to follow the historical evolution of events. Mm-hmm. In the beginning, there was AES, which, as I'm sure you know, was developed in Leuven. Then there was Starkware, who had also an amazing crypto system, but achieving something completely different. And they wanted a hash function that was efficient for their proof system. And they looked at SHA-2 and they looked at AES and they decided, well, maybe there's another option out there that we don't know of, or maybe we can actually design something that improves on these metrics. So they reached out to Leuven, and Tomer and Simon, co-authors on this paper, started working on an improvement over AES called Jarvis. Jarvis is the block cipher, and then you turn it into a hash function called Friday. And the idea is where AES uses a state consisting of 16 field elements, Jarvis uses a state consisting of one field element. But in the end, the evolution is still rather similar, right? It's inversion operation applied to all the field elements, followed by some linear operations. And repeat that. Don't forget to inject the key, and repeat that simple process enough times to thwart all attacks. And they wrote a really good paper showing that it really does thwart all the standard attacks in traditional cipher design. So that was actually received very positively, even by the internet. People started implementing Jarvis without being prompted to, and they started asking, or they even started implementing this over prime fields, even though it had been designed only for binary fields. So there was clearly a big demand for this, but then it got broken. Tomer disagrees, and there is some discussion to be had about the exact complexity of the attack, because we don't know how much memory it will take, and maybe the memory bottleneck will make the attack impossible. But still, there is an attack that the designers hadn't foreseen based on Grosvenor basis. And if you follow the reasoning of the attack, the projected complexity is far smaller than the projected security level.
What's the name of this attack?
I don't know if the specific attack has a name, but it falls into the general category of Grosvenor basis attacks.
Okay.
We can get into what Grosvenor bases are and what they do later on. From my PhD studies, I happen to have seen Grosvenor basis attacks in the context of attacking public key crypto systems. So Tomer and Simon brought me on board to advise on the next member of the Marvellous universe. And then we brought on Abdel, who's an expert on MPC. And then we had so many questions for Eli that in the end we thought it's a good idea to mention him as a co-author. In the end, he wrote some pieces of text that have undergone very little evolution since, but then have engendered evolution on the rest of the text. So it was, once again, a collaboration between people of various expertises. And the clue here is that we revised the design of Jarvis substantially to produce Vision and Rescue. Vision, like Jarvis, works over binary fields. Rescue works over prime fields.
Vision and Rescue, these are the ciphers. This is in the paper. Are
Yes.
these are inventions, basically, with this construction?
Yes.
Okay. Your naming is all starting to have a trend. Also, I looked at the notes. It seems like this is all Marvel comic references.
So it is. And from our perspective, so obviously is the STARK proof system, which in the end was the first and foremost goal for optimization. Seaman is the comic book expert. I don't really know the origins of the names, but I do like the names.
It's all just dawning on me where Starkware comes from. Got it.
Yeah. Although
all this time I've been totally clueless. That's great.
Although at some point we had to generate coefficients by expanding a short seed using catchup, and the short seed is winter is coming.
Oh, so that's a different one.
That's a different universe altogether.
Going cross series here. Crazy. So the kind of these hash constructions and even Starkware approaching like the university and all of this, is this part of the STARKs hash competition? Because I know that they're looking for these new hash functions and that there's some sort of evaluation going on. Maybe, I don't know if competition is the right word, but...
My understanding is that they also reached out to Luxembourg, the university there, and they were also developing Stark-friendly hash functions, and they are the ones that attacked Jarvis. So there is friendly competition going on between Leuven and Luxembourg in that respect. So in the end, we came up with the Marvellous universe of hash functions, and they came up with the Hades universe, Hades paradigm for constructing Stark-friendly hash functions. And then Starkware decided, well, we don't really know how to assess the security of all these functions. Let's just create a competition, and then we can support the argument for security by saying there's been a bounty on these hash functions for this long now. If nobody was able to collect the bounty, that means that nobody was able to break the function, which means it has to be a secure function.
Cool. So you mentioned just earlier this Grosvenor basis attack and that there was sort of a larger topic behind that. Can you explain something more about that?
Sure. Grosvenor basis attacks are based on Grosvenor bases, which are the polynomial algebra equivalent of vector space basis in linear algebra. So in linear algebra, your vector space is spanned by taking linear combinations of basis vectors. And the clue is that the coefficients in this linear combination are taken from your finite field. In polynomial algebra, you get to take polynomial combinations. So the coefficients can be taken as polynomials. And this generates something more general than a vector space. This generates an ideal. Just as every vector space has a basis, and multiple bases, in fact, so too does every polynomial ideal have a basis, and in fact, multiple bases. And the useful basis in linear algebra is obtained through reduction to row echelon form. And there is an analog in polynomial algebra, which is essentially computing the Grosvenor basis. The Grosvenor basis is essentially the same as reduced row echelon form. And it's very, very expensive to do. Unlike linear algebra, computing the Grosvenor basis is prohibitively expensive. It depends on all sorts of things that we don't know. It depends on how you model your attack. So what you do is you specify a list of polynomials, and then you run your Grosvenor basis algorithm, and then the Grosvenor basis algorithm spits out a solution. Except, how long does it take for the Grosvenor basis algorithm to run? That's a very big open question. And we have a couple of ways of arguing this in the paper. But in the end, the truth is we just don't know. Nobody knows. And that's a very important question. And as a result, it's difficult to estimate the security of arithmetization-oriented hash functions.
So one thing I want to say is I didn't realize when we invited you on here how much the topics that you have touched on and covered and worked on kind of intersect with like other works from guests we've had on before or topics that we've been kind of mulling over on this podcast this much. So it was really, really great to have you on. I just want to say thank you for sharing all of this with us. And I know that we've only just scratched the surface on a lot of these topics. I think a question that I would have for you is, where should people go if they want to dig in more on this stuff? Maybe even specifically on this Marvellous hash function universe.
Well, there's the Marvellous paper, which is on ePrint, and it has a couple of references. And for a lot of questions that are still open, I'm afraid there are just no references. That's what it means for a question to be open. So yeah.
You're basically saying, go study cryptography and help us solve it, right?
Exactly. And if you or one of your listeners are interested in maybe coming to Switzerland to work in a secret laboratory of cryptography research, then go ahead and drop me a line.
Oh, cool. All right. We'll put some links in the show notes for anyone interested. All
right. Yeah, it really has been great. I mean, for me, some of these episodes where we focus more on cryptography is a treat for me because it's not something I get that much of in my day-to-day. So I love it. Thank you very much for being on the show.
Thank you very much for inviting me. It was my pleasure, and I'm really happy to see that this formerly arcane field of science is getting people excited, even people who aren't inside the field. And I think the Zero Knowledge podcast is one of the reasons why that's happening. So I'm happy you guys exist.
Thanks.
Thank you.
That's so nice of you. And to our listeners, thanks for listening.
Thanks for listening.